Welcome back. In this lesson, we're going to go a little far away from home and look at other galaxies in the universe. So we've looked at the Milky Way galaxy. Now we're going to look at other galaxies, and it's determined or estimated that there is many galaxies in the universe that we can even measure, as there are stars in the Milky Way itself. So just ridiculous, immense vastness of space. How big it is and how much it contains, how much stuff is going on. It's a very busy place that we know very little about. So let's look at some of. Our largest space telescope is called the Hubble Space Telescope, and it's named after Edwin Hubble, who is probably the greatest of the 20th century astronomers, and some major accomplishments in what he found out about the universe. He was working in California, in Los Angeles, at Mount Wilson Observatory, which I think in the 20s, Los Angeles wasn't as light polluted or air polluted as it is now. And he was looking at he had pointed his telescope to a smudge that you can actually see with your eye, naked eye, right to the left of the constellation of Andromeda. So Andromeda is the back legs of Pegasus, the big square of Pegasus. So it's in the summer-fall sky. In any case, there was a smudge there, and the stars very close together were thought to be some kind of a cluster of stars, some kind of a cluster, but yet it was even more of a smudge than a cluster. So it was thought that this was a nebula. So a nebula, remember, is gases or a cloud of gas and dust that is in an area of space that is either been kind of exploded away from a star or is condensing to form a star. That's the idea. In any case, as he pointed there, he found some variable stars. And because he was able to find these variable stars, he could find the distances of those stars based upon how the timing of its fluctuation. And he was, from all of the various variable stars that he found in that nebula, he determined that it was much too far to be in the Milky Way. And so from this first idea, you have the idea that we do not just have a campsite with a lot of trees around us, but that when we can look at the trees from our campsite, some of those trees are not actually in the forest that we're in, but are in other forests farther away from us. So the whole paradigm of how the universe looks changed in just a moment. So instead of just the Earth being at some central place with stars in 3 dimensions going out into infinity, you had a Milky Way galaxy, which was kind of a home place, a hometown, and then you have large distances to other galaxies of stars. And so this was the first idea that there were other galaxies in the universe. That nebula, which was called the Andromeda Nebula because it was in the constellation Andromeda, is now called the Andromeda Galaxy, and it's the only galaxy you can see with your naked eye. So the amount of light that a galaxy would emit is based upon the amount of stars that are in that. So really the only thing that we could do is take our sun kind of as an example and the light that our sun emits, and then look at the light that's being generated by a galaxy, and then see how many times our sun is that light emitting. And so from those calculations, it's actually estimated that there's maybe 100 billion stars in each particular galaxy, some bigger, some smaller, but the rough idea that you have 100 million or even more than 100 million stars in a galaxy with maybe 100 million galaxies that are estimated. It gives you a sense of scale that you can't really have when you're only looking at your feet. So the idea of just how big the universe is a idea that's expanding, if you will, over this time since the 1920s, when we've had the first idea that we were not just in one galaxy, but in multitudes of galaxies in a hyper-expanding universe. It's pretty amazing. One of the most difficult ideas in the late 20th century that was talked about and still talked about now is the idea that the gravity effects, that what we're looking at as we look at distant objects, we're looking at how the mass that's in that object is affecting other masses around it. So one mass is exerting gravity on another mass and actually making it move in a lot of ways. If you were to take all of the evidence of the movement of galaxies, what is causing this movement, there isn't enough mass to form the gravity that would cause the movements that we are seeing. And so the proposal is that there is matter that is not visible. In fact, most of the gravity required would have to be from this dark matter. It's called dark matter. It's thought that the dark matter is a different interaction or configuration of the subatomic particles that make up, say, a neutron or make up a proton. So as they interact, some will be visible, some will be invisible, and so some of the matter is not to be seen, but is at least to be measured in terms of what its mass is doing to other masses. Pretty amazing idea. That's about the extent of my knowledge about dark matter, sorry. Different galaxies, just in terms of their shapes, have been seen through the telescopes. Some galaxies are not spiral. They're not flattened. They're just basically globes of a star density. Now, still with very many stars, huge bit of space, but basically acting like a foggy blob of stars. These are called elliptical galaxies, very similar to the ellipse of the planets going around the sun, where you have not just a total sphere, but kind of a bulgy sphere. Some galaxies don't have a distinct shape at all, and they're referred to as irregular. Some are elliptical, are spiral, like the Milky Way, and some are barred spiral, like we mentioned before. Now, if you were to make a map, or basically put your full address on an envelope, after you say planet Earth, you would have to then say solar system, then Milky Way galaxy, which is our locality. Then those local galaxies that are closest to us are called the local group. The local group of galaxies, about 40 galaxies. Andromeda is in that local group of galaxies, and so you can then have larger clusters of galaxies in the local group. So you basically have groups of groups, or globs of globs, if you want to think about it this way. So you would end up with, local group and then large clusters, and then you are thought to even have clusters of clusters. Now, this is amazing, this three-dimensionality of the universe to the extent that we know it, because we have to be reading energy waves that are coming from these objects through immense distances of space. And some of these objects don't travel. I mean, the speed of light is a fixed amount. It's only 3 times 10 to the 8 meters per second. That's as fast as energy travels through empty space. So just the edges of the universe being so far away, can we even detect it? Is it possible? Are we going to be eternally learning about what our universe looks like? It's pretty amazing. The last idea here is that if you were to look at these galaxies, you're going to get the Doppler effect that we mentioned before, the red shift, where these frequencies are heading down towards the red end of the spectrum, and you induced by that or deduced by that it is moving away from you. Well, every galaxy that you look at is moving away from us. Either they hate us, or the proposal is that all of them are moving away from each other. So the easiest idea that I could express would be put some dots on an empty balloon and then blow up the balloon. As you blow up the balloon, all the dots are not just moving away from each other, but all of the dots are moving away from every other dot. So that's an expansion. So the universe is not a static fixed volume, but is actually continuing to expand at some boundary, at some frontier, where there is no universe, empty, open nothingness, with a universe expanding into it. It's a pretty amazing idea, but that's the idea of as time ticks, so there's a space-time idea, space is actually getting bigger and bigger and bigger. So we'll see some of that, what that implies in a later lesson. And then this universe is expanded. If you were to look at a graph that could be induced by this, there is a kind of a mathematical formula for what we've been able to see, which is called Hubble's Law. And so Hubble's Law is one of the math formula that's used as we're looking at this idea of expansion, universe expansion. Just like stars can emit pulses of energy, galaxies have been known to emit pulses of energy. And so these are radio galaxies, where radio galaxies meaning they're sending out energy waves in pulses, kind of shock waves, pulsing waves, like a pulsar star, only it's a pulsar galaxy. So just the mystery of what's going on in the universe is pretty amazing. One of these pulsating galaxies is called a quasar. So these are very far away galaxies that are sending out pulses of energy. It's pretty amazing.